Welcome to This Explainer. Today, we're diving into computing paradigms in modern computing. We're going to take a chronological journey together to totally demystify modern computing architecture. Have you ever wondered how we actually got to the point where all our data, apps, and services just seamlessly live out there in the ether? Well, we're going to break down the specific computing paradigms that paved the way, step by step, to give you a crystal clear understanding of the digital foundations our modern world is built on. Let's get into it. So let's kick things off with a massive question. Where did the cloud actually come from? And will it completely replace traditional computing devices like your high-powered desktop or localized servers? You see, understanding this evolution isn't just about geeking out over tech history. It's literally the master key to understanding exactly where our entire digital future is heading next. The cloud isn't just some sudden magical invention that poofed into existence overnight. It's actually the logical, inevitable result of a fascinating quest for limitless, frictionless computing. It's a brilliant convergence of several core ideas that solved major human and business problems, building upon one another over decades. Think of this evolutionary timeline as a giant staircase. We started way down at the very bottom with early time-sharing computing on massive, room-sized mainframes. And from there, we climbed. We climbed through peer-to-peer networks, advanced web services, all the way up to autonomic computing, and eventually the cloud. Every single step up this ladder represents a crucial technological leap in how we share and manage processing power. We're going to look closely at the major steps of this journey right now, so we can understand exactly why we needed to keep climbing. First up is the foundational stepping stone of the whole thing, distributed computing. This is a model where components of a software system are shared among multiple independent computing systems. But why did we even need this? Well, as computational tasks grew way too massive for any single machine to handle without crashing or, taking years to calculate, engineers had to totally rethink their approach. The goal became simple but incredibly powerful: achieve faster execution through intelligent task allocation. So instead of forcing one giant expensive machine to do all the heavy lifting, you get multiple independent machines to work together on a single problem simultaneously. It's the ultimate divide and conquer strategy in the digital world. Now, that divide and conquer strategy quickly evolved into cluster computing. This took that distributed idea and centralized it physically for maximum speed and control. A cluster uses homogeneous hardware, meaning computers that are essentially identical to one another, sitting in the exact same physical room or local network, and it ties them tightly together. Think of a cluster kind of like a team of identical horses strapped to the exact same carriage, pulling perfectly in unison under one single driver. By coupling them so closely, they function and present themselves to the user as one incredibly powerful system. You get centralized management, centralized scheduling, and an entire room of computers acting as one single brain. But what happens when you need even more power than a single room can hold? Next, we introduce grid computing, which expands this idea globally by connecting completely different types of machines spread across various administrative domains. Think about massive global challenges like deep climate modeling, simulating black holes, or mapping the human genome. These are tasks so unimaginably immense that they require borrowing idle compute power from all over the globe. So instead of being stuck in one room with identical machines, a grid creates a decentralized, loosely coupled system. You might have a supercomputer in Tokyo, a server farm in London, and a cluster in New York, all working together on the same problem. They're heterogeneous, meaning they have completely different hardware architectures, but they're linked together across the internet to share resources. There is a really fascinating contrast between these two approaches. A cluster offers the tight, localized control of a single owner, with identical nodes acting rapidly as one single entity. A grid, on the other hand, sacrifices that tight local speed and centralized control to gain massive, decentralized scale. In a grid, you have autonomous, independent nodes owned by completely different parties, communicating loosely over wide area networks. The grid was a monumental step forward because it proved for the first time that we could harness collaborative computing power across completely different organizations and borders. Okay, so as the physical networking of grids evolved, the business models surrounding them had to evolve too. Enter utility computing. This was a massive conceptual leap that completely changed the tech industry forever. It focuses on the economic benefit where users no longer need to own the hardware outright. Instead, they pay a service provider only for the specific resources they use based on an on-demand, pay-per-usage billing method. This was the exact moment massive capital expenditure, like buying million-dollar servers up front, turned into operational expenditure, where you're basically just renting power by the minute. This decoupling of hardware and software is the exact insight that allowed modern internet startups to exist and scale globally without needing massive initial funding. It was a total game changer. The underlying concept here operates on a brilliant real-world analogy. Utility computing is the packaging and delivery of computing resources exactly like traditional public utilities, electricity, water, or telephone services. Think about it. A century ago, if a factory wanted power, they had to spend an absolute fortune to build and run their own local power plant. But when the electricity grid arrived, they just plugged a wire into the wall and paid a monthly bill for the exact wattage they used. Utility computing did the exact same thing for processing power and data storage. You just plug into the network, and the power's there. And that finally brings us to the absolute pinnacle of this evolutionary quest for limitless computing: cloud computing. This is the delivery of on-demand computing services, including everything from servers and storage to databases and networking directly over the internet. It provides faster innovation, incredibly flexible resources, and massive economies of scale. We can define the cloud as the ultimate synthesis of all these earlier models we've talked about. And the real magic trick here is virtualization. It's a technology that completely hides the underlying physical hardware from you, the consumer, making the whole transition seamless. You never know, and honestly never need to know, what physical machine is actually running your code. When we look at all these models side by side, the evolution becomes crystal clear. The cloud basically borrows that concept of total distribution from the grid, but it utilizes heterogeneous commodity hardware owned by massive corporate providers. Let's break it down. A cluster is one location and one owner. A grid is many locations and many owners. The cloud, however, manages hardware spread across multiple global data centers, but those resources are generally owned and managed by a single mega provider. Think Amazon, Microsoft, or Google. And they act as a single unified service for you, the end user. But the true game changers here, the features that completely separate the cloud from those older cluster or grid models, are rapid elasticity and on-demand self-service. Imagine a small company's website suddenly goes incredibly viral overnight. With the cloud, their systems can instantly and elastically expand their processing power to handle the massive surge in traffic, completely preventing a crash. And then it automatically shrinks back down when the spike is over, so they save money. You don't ever need to call a technician to rack new servers. It is entirely on-demand, self-service, and instantly measured for billing, just like water flowing from a tap. Because ultimately, the cloud wasn't just one solitary breakthrough. It's a beautiful, complex harmony of all these distinct computing methodologies coming together at exactly the right time in history. It took the ubiquitous access derived from grid architecture and combined it perfectly with the on-demand delivery model from utility computing. It takes the philosophy of a dynamic, intelligent system and maps it directly to methodologies like hardware virtualization, service-oriented architecture, and Web 2.0 applications. It is quite literally a symphony of decades of human problem solving. So, to summarize our entire evolutionary journey, the cloud is simply the ultimate mashup. It perfectly integrates the absolute best features of all these preceding paradigms into one seamless, powerful experience. It's built entirely over distributed computing principles to efficiently divide and conquer tasks. It uses cluster computing's ability to pool resources for centralized power. It inherits grid computing's ubiquitous access and distributed architecture to link data centers worldwide. And of course, it relies entirely on utility computing's on-demand, pay-per-use business model. Without that, the massive commercial cloud industry simply wouldn't exist as we know it today. Which leaves us with a genuinely fascinating thought to ponder. If cloud computing is really just the evolutionary equivalent of plugging a factory into a public electricity grid, taking something immensely complex and making it a simple, invisible background utility, what invisible utility will we be plugging our minds into next? As artificial intelligence and quantum computing continue to mature, the next massive step on that evolutionary staircase is already being built right beneath our feet. Thank you so much for exploring the architecture of our digital world with me today. Catch you on the next explainer.